Greetings to the International Space Elevator Consortium and the academic challenge judges. I am Mohir Kapoor, representing the Astronomy Club Manipal from the Manipal Institute of Technology, Manipal. Guided by our mentor, Dr. Purnima Panduranga Kundapur, our team presents a new architectural framework, Space Elevator-Enabled Infrastructure for Persistent Planetary Defense and Orbital Systems. Our core thesis is simple. Current planetary defense is constrained by the economics of rockets to be episodic and reactive. We propose shifting to a persistent infrastructure model, enabled by the space elevator, that transforms defense from a high-stakes emergency response into routine automated logistics. To understand the solution, we must first isolate the structural bottlenecks. The current paradigm relies on chemical rockets fighting gravity drag, where every mission starts from zero velocity at Earth's surface. This is high thrust, but energetically inefficient. In contrast, the space elevator allows us to mechanically lift payloads to high altitudes for tangential release, utilizing the Earth's rotation to grant immense orbital energy without expending propellant. This shift is not just about fuel, it is about changing the fundamental physics of deployment. High launch costs create a redundancy wall, where the cost of achieving greater than 95% mission reliability becomes prohibitive. High transport costs enforce a, quote, procurement constraint, preventing asset prepositioning. Current LEO and GEO costs are very high. The current monolithic architecture has a 10% probability of mission failure. The reliability paradox, driven by economics, forces all eggs in one basket designs. In contrast, a theoretical swarm architecture achieves a 0.001% probability of failure by distributing mass. There is a temporal propulsion mismatch. Required launch prep takes months, but short-warning threats like 2023 CX-1 are detected hours before impact. The current architecture cannot mitigate short-warning threats. Detection only enables public warning, not deflection. Propulsion constraints limit high-velocity intercepts on short notice. The rocket equation prohibits intercepts due to low specific impulse for chemical rockets and low thrust for electric propulsion, which cannot achieve intercept in under 6 months. The absence of forward infrastructure creates a solar glare blind spot. Ground-based surveys cannot observe the region near the sun. Out-of-the-sun threats are detected only hours before impact, meaning every response starts from a standing start on Earth. The current architecture has scalability and parallel response limits. Missions are serialized. If 2 concurrent threats appear, the system must prioritize one and abandon the other due to bottlenecks in resources like launch ranges and specialized inventory. Transitioning to space elevator economics drastically reduces cost to GEO from $15,000 per kilogram to $220. This 10x to 150x reduction shifts the architectural constraint from procurement to operations, reaching the viability threshold for massive infrastructure. The space elevator enables the economic viability of external redundancy. Transport cost for a 5-ton monolith is $75 million versus $1.1 million for a 50-unit swarm. Redundancy moves from internal complexity to external, simple, disposable spacecraft. Apex anchors bridge the temporal gap by pre-positioning assets outside the gravity well at 100,000 kilometers. Instead of launching on warning, which takes months, we can release on tasking, reducing prep time to hours. The response becomes logistical, not developmental. Persistent staging at the apex anchor provides high orbital energy and tangential velocity. This allows for Delta-V accumulation, using high-efficiency electric propulsion to build velocity before threat detection, bypassing gravity drag and atmospheric loss. The permanent forward-sensing geometry uses sensors deployed at the apex anchor and Lagrange points for overlapping 360-degree coverage. This eliminates the solar glare blind spot, allowing detection times to move from hours to days or weeks. Forward-deployed command and characterization utilizes Edge AI on the apex anchor for automated decision-making. Loop B, the orbital brain, provides sub-second latency for high-velocity intercepts, beating the light-time lag of Earth control. Loop A. Scalable parallel response operations are enabled by continuous ascent and automated assembly at the apex. This infrastructure can deploy multiple vectors, addressing 14 to 79 metric tons per day. Swarm intelligence can handle multiple concurrent threats without resource contention. In conclusion, the architectural shift moves from episodic and fragile rocket-based systems to a persistent, resilient, and logistics-driven elevator-enabled future. The space elevator converts planetary defense to routine, automated logistics. This brings us to Part 2, the implementation. A structure extending 100,000 kilometers through the atmosphere, LEO and GEO, cannot be managed by human operators alone. The operational dynamics exceed human coordination limits. We propose integrating artificial intelligence not just as an add-on, but as the structural requirement, the enabling layer that creates a responsive, global resilience machine. We define this as the operational nervous system. Current command loops are constrained by human reaction times. We propose a bounded autonomy architecture. Here, the AI manages high-frequency control loops, millisecond tether dynamics, and traffic scheduling, while humans retain strategic authority over escalation thresholds, such as interceptor arming. This compresses the detection-to-tasking latency from days down to minutes, creating a unified state vector across the entire infrastructure. The backbone of this system is the tether itself. We utilize distributed fiber optic sensing cores embedded along the ribbon. These generate terabytes of raw backscattered data daily. It is impossible to downlink this volume. Instead, we use edge compute nodes spaced along the tether to perform local feature extraction. We employ LSTM, long short-term memory networks, to detect precursors to flutter and resonance before they become structural failures. This monitoring feeds directly into physics-informed predictive control. The tether is subject to nonlinear dynamics, atmospheric drag, Coriolis forces from moving climbers, and thermal shock as it passes through Earth's shadow. Our control laws use hybrid learning, combining finite element simulations with real-time operational data to actively dampen these vibrations by adjusting climber speeds. This ensures we never violate the safety envelopes of the carbon nanotube material. With the structure secured, we optimize the flow. Traffic is managed like a packet-switched network. Using constrained optimization algorithms, the system balances the ascent of commercial payloads against the urgent priority of defense assets. In a threat scenario, the AI dynamically reprioritizes the, quote, packetized flow, flushing commercial traffic to clear the line for defense mass, ensuring we maximize the 14 to 79 metric ton daily throughput estimated by ISEC studies. To execute this, we deploy the Orbital Brain. This is a tiered compute architecture. While heavy model training and simulation occur on ground-based petaflops clusters, tactical inference runs on the edge. Climbers and the Apex Anchor host accelerators, sized at 10 to 100 TOPS, tera operations per second. This ensures that even if the link to Earth is severed, the Apex station retains the intelligence to detect threats, task interceptors, and maintain stability. When deployed, our interceptors operate as an autonomous swarm. Using multi-agent reinforcement learning, they self-organize. If one unit is lost, the others instantly recalculate the optimal geometry to ensure the asteroid is deflected. It is a self-healing mission. In the terminal phase, facing relative velocities of 10 to 30 kilometers per second, ground control is impossible due to light lag. Our interceptors use onboard sensor fusion, combining optical and infrared data through extended Kalman filters. They execute fire-and-forget maneuvers with sub-meter precision, guided by vision transformer models that have been hardened against solar glare and adversarial noise. Critically, we do not need to launch these interceptors fully formed. The elevator enables in-space assembly. Robotic arms at the Apex Anchor assemble modular propulsion buses and impactors delivered incrementally. This decouples spacecraft design from the volume and vibration constraints of a rocket fairing, allowing us to build massive, fragile structures that could never survive a launch from Earth. This capability extends beyond defense. The same logistics backbone makes space solar power economically viable. The elevator lifts the massive tonnage required for solar arrays, which in turn power the elevator and the Earth. It enables industrial-scale biological manufacturing in microgravity, producing tissues and pharmaceuticals in continuous orbital foundries rather than experimental batches. But ultimately, for planetary defense, the metric that matters is speed. We compress the OODA loop, observe, orient, decide, act, from years to mere days. We move from a design-then-launch model to a detect-then-release model. This system is resilient. With distributed authority and physical redundancy, there is no single point of failure. It is designed to survive. In conclusion, planetary defense should not be an isolated, frantic mission. It must be part of a unified industrial ecosystem. The space elevator provides the backbone that unites energy, industry, and defense into a single sustainable expansion of human activity. By combining the mechanical advantage of the space elevator with the cognitive speed of artificial intelligence, we do not just improve our odds of survival, we make planetary safety a routine utility. This is resilience through infrastructure.